Hello, you. Welcome back. Today, we're reading one of my favorite articles of all time. This is from 2011, and it's timeless. Talking about Up and Down the Ladder of Abstraction by Bret Victor. Now, if you don't know who Bret is, Bret has this blog, Worry Dream, and he writes some of the most insightful blog posts about visualization, about interacting with systems. He has about 5 talks on YouTube. I've watched all of them multiple times. He's absolutely brilliant, extremely insightful in just interactive visualization, in just the clarity of thought that he has about designing systems or designing ways to explain complex systems. And this is one of his masterworks. You can watch the YouTube videos of him speaking. I go back every now and then, and I learn something new every time I rewatch them. Now, this article right here is an example of how do you create a system, or how do you think systematically about creating interactive visualizations. And it starts with a quote by Richard Hamming, which Bret quotes a lot and looks up to, and also wrote the introduction, I think, to a new re-release of this book. Quote goes, "In science, if you know what you're doing, you should not be doing it. In engineering, if you do not know what you're doing, you should not be doing it. Of course, you seldom, if ever, see either pure state." This is also always the case in machine learning. You tend to be doing a bit of engineering, and then a bit of science, and then a bit of engineering, and you veer between the two. Bret asks, how can we design systems when we don't know what we're doing? And this is part of the mystery of designing an interactive visualization, where you're exploring something, you're exploring a data set, you're exploring a system, you have questions, but you're supposed to build things to glean a little bit of insight to answer some of these initial questions, and then introduce new questions, and then maybe you build something else that goes into explaining them. The most exciting engineering challenges lie on the boundary of theory and the unknown. Not so unknown that they're hopeless, but not enough theory to predict the results of our decisions. Systems at this boundary often rely on emergent behavior, high-level effects that arise indirectly from low-level interactions. And here in the second column, it starts to lay down the major outline for this article, a ladder of abstraction. How do we explore? If you move to a new city, you might learn the territory by walking around, or you might pursue a map. But far more effective than either is both together. So you can be here on the ground, walking around and knowing the shop fronts and how the streets look, but you can also have a map that has a high-level view of the entire terrain. And then if you have them both together, you have better understanding. In this article, present a simple system and then a few ideas about how to create interactive visualizations to understand them. So the central idea here is moving between levels of abstraction. The author says, I believe that an essential skill of the modern system designer will be using the interactive medium to move fluidly around the ladder of abstraction. And I want you to think about the word system here a little bit more generally. So this doesn't have to be just an operating system or a software system. You can think about companies as systems. You can think about maybe economies and interactive visualization designers, or anybody who works in creating dashboards. In a lot of companies, that's called like business intelligence, but it also falls under data analysis, data science, and a lot of them have to explain and understand complex systems. And so going through this article, it would be useful for you to think about the systems that you think about that are closer to your areas of expertise and the areas where you are mastering something or you have a unique skill And if you understood a system a little bit more, you would be more successful or more productive. All right, here we start to look at the simple example that will guide this interactive article. So it's a simple car simulation. The goal is to write a set of rules that allow a car to navigate roads, such as the one on the right. So you have this car here and the road, and then what kind of system, a very simple couple of instructions to tell the car how to stay on the road. Now, this example is much simpler than, like, say, a self-driving car. So we don't need sensors and LiDAR and complex equipment. We have a simple sensor that tells you you're either on the road, you're left of the road, or right of the road. So very simple sensor that feeds this information to the system. And based on this state, we can tell the car either to turn a little bit to the right or a little bit to the left or continue straight. So very simple example, but just to communicate the idea. And then the simplest example here of an algorithm, we can say, okay, if you're on the road, then continue going straight. If you're left of the road, veer a little bit to the right. And if you're right of the road, veer a little bit to the left. So you go back into the road. And so this is a view of how this algorithm might look. It says at each step, so assume you're always in a loop, you're always moving. So move forward 1 pixel, and then based on whether you're straight or right or left of the road, either turn right or turn left. And here we have a video of how that algorithm works. So it runs a simulation. So we look at that again. It felt it's on the right, so it veered to the left, and then it went all the way to the left, and it got to the end of the road using this simple and basic algorithm. Now, this video here is a visualization. It's an artifact gives you a sense of the system, but you have to wait for it to play out so you can understand all of it. It unravels through time. Can we do a little bit better to understand this system? Here, the author presents an interactive version. So instead of playing the video through time, he's introduced this slider that you can move to see the car at each part of the system. So you can interact with the system to zoom in and focus maybe on specific areas where you find are more interesting than others. And that gives you a little bit of control. So you don't have to wait for, let's say, the 2 seconds and watch the video every time. And this gives you a little bit more control. And this, you can click on it and it holds at wherever you've clicked. And the section closes by saying a designer needs direct interactive control over the independent variables of the system. We must not be slaves to the real time. Now, we're not only observers of systems. A lot of us are also, we explore systems, we design systems, we can influence systems. You can influence the system of how your company gains customers or clients. Or how your model classifies a set of inputs. And so a next level here of understanding is for us to add some controls to control the algorithm. So this new and updated version of the interactive visualization also continues to have the time slider where we can observe the system at any step, but also has this new slider that controls it has a range of movement of how to turn left and right, and you can control it. So by default, the initial state of the system is that you turn 2 degrees to the right if you observe that you're left of the road. So let's see how that affects the system if we change it. So here, this is where you see the system moving to the right, to the left. And notice that it's moving 2 degrees at each step. So it's not just 2 degrees from here. It's So this is 1 step, 2 degrees. And you continue to be on the right side of the road. So turn left, 2 more degrees, 2 more degrees, 2 more degrees. What if we change that a little bit? Let's hold this here, and then let's say we want you to move a little bit more drastically to the left. And so here you can start to see that the turns are a little sharper, and the car stays outside of the road a little bit less because it adjusts quickly. And you can hold the time steps here and adjust these and observe just various permutations of how the system would have worked. So we can bring it back here, and then we can say, okay, we don't want you to turn ever. So the system is just a car that goes straight all the time. So here, goes straight, never turns. Or we can tell it to turn to the left 10 degrees, which is a little bit too drastic. So it's going to be, ping-ponging. So it's a sharp turn, sharp turn. That's not unreasonable. But then notice that there's also this design decision of limiting this to between 0 and 10 degrees. Another really beautiful touch here, and there are a lot of these subtle things that the author does not point to but uses, is that, try setting the turning rate to 0. And when you click on 0, see, it looks like a hyperlink. And when you click on it, it just resets this. So this is a way of tying the narrative of the article to the interactive visualization. And we hope to see this more and more in notebooks, like Jupyter notebooks, and these kind of communication and exploration mediums. But Bret is ahead of his time. Next, we can abstract over time. And here you can see a small icon of a ladder. And where we started in where did we start? We started on the bottom, on the floor, the bottom rung. And now when we talk about abstracting over time, we have gone 1 step higher in the ladder of abstraction. So the basic idea here is that the interactive visualization here can be updated so that it doesn't just show one screenshot, one snapshot of time of where the car is. No, you can go a little bit higher, kind of like you're walking on the ground, but now you have a map. And you can draw the entire path of the car so a person can see all of it in just one time. And so this is the initial algorithm of 2 degrees. This is the path that the car would have taken. And in just one glance, you get all of the information that you would have had to wait 2 or 3 seconds watching that video to see. But not only that, this kind of view gives you the ability to add more controls. And so if you change the turning ratio or angle, you can update the interactive visualization can be updated to show the new path that the car would have taken. And so if it's 0, the car goes straight. If it's slightly more, the car turns this way, this way. And so you can, in a very short time, by sliding over this slider, you can see snapshots of multiple systems, all in just the time that it took to understand one system. And so you're taking a step higher in the abstraction, and you're seeing multiple states of the system. And that's absolutely brilliant. So to think about what happened here, we had the slider for time that we could control, but now we're just showing all of its value. We're abstracting that parameter, and we're showing all of its values here as a line. The author says, by abstracting over a variable, we've taken our first step up the ladder of abstraction. Enjoy the view. It's kind of like that map view that you're seeing from the top. Then stepping back down. And this is a comfortable section that you don't need to always go up and get more abstract in your system. You can step up and down, and you can view multiple states of the system, but also make sense still of things that are more real. And here it reintroduces the time step. So you can see the abstracted version of the line, but you can also impose the car and the time variable here. So If that's something that is of interest to you, you still have that ability to, once you step down and abstract a variable, you can go down and maintain the same control and allow the user to explore the system at that lower level of abstraction. Here's another example of these clickable examples or moments. So it says, try cracking the turning rate up to 8 degrees or so. So when I click on this, it jumps over there. And then inspecting the car's behavior as it makes its first 2 turns. So this one and this one. It almost pivots in place, that it's doing unnatural sort of movements, and this visualization is giving you the ability to discover that. Now we're ready to take one more step up the ladder, which is abstracting the algorithm. And the idea behind abstracting the algorithm is to say, okay, in here we had the car only and 2 variables. So we abstracted this first variable by drawing this red line. But can we abstract this variable also of the algorithm? Can we show one view that shows multiple states of both these variables at the same time? That is the second step here up the ladder of abstraction. And the idea here is that, yes, so instead of drawing just one red line, let's draw the line where the value is, the angle is 0, and then where it's 1, I guess, 1, and then 2 and 3 and 4 and 5, and superimpose all of these, and draw each one of them, make it a little bit transparent. So by overlaying a bunch of them on top of each other, you see the states where a lot of systems overlap. And here are a couple of ways to highlight how that is in the shape. So areas where it spreads apart and areas where the various states seem to have similar behavior. Another visualization here. So the article makes the suggestion that you can have you can visualize these abstractions in multiple different ways. And this is one of them. But another one is that we can zoom in on a metric. So if there's a specific metric that we care about, we can visualize that metric for all the various states of the system. And in this case, it is how many steps to the finish line. So how many steps does the car take in this shape to go from point A here to point B there? And you can see when the turn rate is around 1, it takes the longest time, or, takes too many steps. But then around 0 and some of these, so this is the least time that it takes, but it stays outside of the road for a while. And then here it flattens out, and you can pick any of these values where the car stays on the road and finishes in, let's say, 450 steps. And then now that we're 2 steps up in the ladder, we can go back down and have another sense of this new abstraction that we've created, where we have the image where we've superimposed all of the variables or all of the values of the turning rate, but you can have an interactive system here that you can set the number of degrees, and it would highlight to you where that specific value is on both of these shapes. So where the trajectory is, and then how many steps would each of them have. And so this is still being abstract and viewing the entire system, but also giving a way to control and look a little bit more in detail at the specific states of the algorithm. Then again, this storytelling here is incredible, where it says, compare the trajectory of 6.5, you can see this jumping here, and then to 6.6, you can see the system updating and this jumping to indicate. If this wasn't jumping, you wouldn't have noticed that small sort of movement of 2 pixels. So the attention to detail here, something like this is made with so much love that it's just absolutely inspiring. And so this is a great spot to let you continue to explore the article on your own. It goes on with a couple more levels and ideas But I think this was a good, gentle introduction to maybe the first half or third of the article. I invite you to watch all of Bret's videos. I'll link to them and this article and the blog down in the comments. And then after you've read all of that, you can come here and control the car, and you can go up and see the levels of abstractions that we've learned. So you're down here, you see a car, you take one step up and you see the line of where the car is, and I'm still controlling it. It's incredible. And then you can go up and you can see the various, so here we abstracted the time slider, here we abstracted the time slider and the algorithm turning rate slider. And then here, there's a lot more complex ideas that are just as interesting and fascinating. And I invite you to read on and think about applying some of these ideas in your work, and share them with us. I hope you've enjoyed this. See you in the next video.